Welcome to the Sunfiber channel. Today with me is David Jensen, who has been working on asteroid restructuring. I'm going to have a nice little discussion about that. But first, David, could you tell us a little bit about your background, about how you got into the space industry?
Sure, Alan. I'll date myself a little bit. I was around when the first moon landing occurred, and of course, Star Trek started, and I'll also mention the movie 2001. I was a very young boy at that time, but I do remember them and was very interested in it from more than the space, more on the computers and the communications that they were using and all the
Oh, yeah.
technologies that they had. And the other thing that happened right about the same time in the 70s, the book, The High Frontier
Yep.
by O'Neill, and Ringworld was another interesting book, David Niven, science fiction, but they talked about huge structures in space. And I remember talking about those space structures. And so those types of things really intrigued me at that age, but it was the technologies that I targeted in my career.
Right.
In my career, I had 40 years of different computer technologies and was very lucky. I was able to do software and hardware and systems and led teams of people on various technologies. The 40 years went by fast and got a bachelor's degree and a master's degree in EE.
Oh, yeah.
PhD, learned how to do research, and that was in computer science. And it was a hardware and software type of PhD study with a lot of discrete event simulations. I mentioned some of those things because it really comes back on some of the work that I've done in the space settlement area. So all that, had a great career, a lot of inventions, actually got products out the door with companies. I worked for a small company, some people may have heard of it, International Business Machines, and I got a printer out the door as an example, helped get a team getting a printer out the door. Worked for Rockwell Collins most recently, which is avionics, where they worry about, and military, so they worry about crypto, and they also worry about avionics safety. So redundancy and fault tolerance, all those things come into play. And if you're listening to all these technologies, all of them are very relevant to space settlements.
Yep.
So I had a great career, was enjoying my work, but I could retire. So I decided I'm going to retire. And this was almost 10 years ago. And what I decided was I wanted to keep doing some technology work. So I went back to space settlements. So the last 8 to 10 years, I've been doing the research, just like I did with the PhD and with various programs that I've done. And I've been focusing on space settlement.
Could you give us an overview of what you mean by asteroid restructuring?
Sure. Restructuring, if you look it up, means converting a physical object from one form to another. It's about that simple. I was reviewing some of my notes and some of my references from my paper. There's a paper that was called Ramos. They were going to send a probe to an asteroid and build mechanical automatas, very little electronics, and proceed to fire off parts of the asteroid and send it back to Earth or to a Lagrange point.
Right.
The whole project was called Ramos, which stood for Restructuring Asteroids for Mechanical Automata.
So this was
another word. It was NASA funded. It was not to build digital electronics, not to build advanced technology, but to take the regolith and proceed to turn it into mechanical devices. And you could think about, okay, well, you want to do a GPS, you want to be able to keep on a course. Well, you build a flywheel, and that a gyroscope, and that can provide you navigation. And you can think about, oh, I want to have a program. Well, you could build, you can't build paper, but you could build a card with punches in it out of glass or out of ceramics. So they had a complete plan on how they were going to build all these different contraptions and use it to power and navigate the asteroid back to Earth.
Okay.
Also, how are they going to use for propulsion? Throw
Yeah.
rocks off of the asteroid. You throw it one direction, you go the other. They were not going to use a mass driver, I don't believe, because that requires electronics, magnetics, refined metals. I think they were going to do a catapult type of operation to
Okay.
send things off. Quite inefficient,
Yes.
but you've got a lot of asteroid. They were going to target like a 50 meter to 100-meter size asteroid, and they were going to probably end up using 1/3 of it as
As fuel.
propulsion material to come back.
Right.
So interesting. But I tell that story because they were using restructuring, a good word for taking an asteroid and converting it into a space station, something completely different.
Yeah.
And it's still all the same physical regolith, the same physical components are going from the asteroid into the space station. I'm not counting on supplies from Earth or
Yeah.
lunar material or other things, just strictly the seed package, the probe that lands, and the material from the asteroid.
Okay. You alluded to what you were going to be building with this. It was a space station, like a Stanford Taurus type space station, or bigger.
In fact, I'll mention the paper. It's a 60-page paper.
Yeah.
And if it's okay with you, Alan, let me take just a little step back about the
Sure.
paper. Okay.
But
The paper, just at a very high level, it's a archive paper, not peer reviewed, but I wanted to get a lot of ideas out there and have some feedback from people. I'm retired. I'm pretty much by myself. I got a few people that I exchange ideas with because I put this paper out on archive.
yes.
When I started, I thought, okay, I'm going to try and create a paper similar to the NASA paper on space settlements. I think
Yeah.
it's their special projects 413, and it's called Space Settlements. And that paper, it's so detailed. It has all the information you could possibly want. If you want to learn how to build a space settlement from a historic point of view, you should be looking at that paper. So that paper, I started looking into building a space settlement, and it turned out what I was collecting was very similar to that paper. So I said, oh, I might create a book. So I've actually collected, I have a 600-page book right now of
Okay.
all the detail that I had collected in the same fashion that I did a PhD study. It's at that level, the research that I did.
Yeah.
So
Okay.
I said, well, I want to get things out there. So I took the 600-page book and I consolidated it down to a 60-page paper. So
Yeah.
every page in my archive paper actually represents about 10 pages of material that I had.
Which is normal for a book, from what I understand.
Okay, so I thought this would be fun. So the paper, it represents a whole set of different things. 60 pages, I talk about what asteroid would you want to go to?
Yes.
And I use an approach similar to what they used for the OSIRIS-X mission. They had a process on how to select Bennu asteroid for their mission. So I used their approach with my own metrics and selected
Yeah.
a different asteroid. What kind of geometry? What kind of space station do you want? That's what
Yeah.
prompted this was your question of what geometry, like a torus. So I investigated, I'll say just like they did in the NASA paper, 4 different geometries of space stations: a sphere, a torus, a dumbbell, a cylinder. And if you're into the space station, you can probably think of stations and projects and even science fiction shows that have had different
Yep.
types of space stations like that. As you start getting to bigger size space stations, all of them work pretty good. They're all very efficient. But I did select with a little bit of margin, it was a little bit better, was a torus station,
Okay.
which is like a donut.
Yep.
What I would have loved to just have said the paper has about 5 different parts to it, and that includes the asteroids, the station, robotics,
Hmm.
which is a very big part of the paper, and then future work. So there's a lot to the paper.
So,
And
yeah, speaking of the robotics, how do you deal with radiation? Because computers don't really work really well in presence of radiation.
yeah, 3 different ways that I
Okay.
deal with that. There are radiation hardened electronics that are used extensively in military equipment and in space equipment. It doesn't perform as well as the microprocessor, your laptop, but if you still have microprocessors, you still have memory, it does work. You can also shield it a little bit, as you said. In fact, I just read a Japanese company had just announced some new kind of material, a new coating that you could put on electronics and dramatically reduce the amount of radiation that would hit the memory or the microprocessor. The technologies keep advancing, and universities now send up small satellites and they use commercial technology. Initially, people were saying, oh, well, this is silly. You're going to launch it, the radiation, it won't even work for a day up there. Well, guess
Yeah.
what? They're working for weeks, months. I mean, it is bad, the radiation, but it does tend to keep working. And so a little bit of fault tolerance, you have two microprocessors running
Mhm.
on your system. Microprocessors are relatively cheap compared to the launch costs. So you
Yeah.
double everything and you take the two results and you compare them to say, are they the same? Did you get a glitch in the system? This is how you do avionics electronics is you do dual redundancy or even triple redundancy because you
Yeah.
don't want a glitch to happen when you're doing your landing on a aircraft.
I seem to remember like on the shuttle there was like 5 computers.
You have to have some kind of a good voting mechanism, I'll say.
Yes.
And there's also actually designing for the fault tolerance.
Right.
So one of my patents actually is how to improve error correction code for memory when they start getting hit by radiation.
Oh,
They
okay.
call them NSEU, neutron single event upset. So
Okay.
neutrons or small particles will hit your
Yep.
silicon, your memory cell, and either cause it to charge or discharge, depending on what kind of material your is it an NMOS or a PMOS? What kind of material is your memory made from? But either way, you have one cell that gets discharged or flipped. And so studied that quite a bit and actually came up with a different scheme for dealing with those single event upsets with an error correction code that added very little cost to your error correction code. Some Someone who's been studying error correction codes might understand what I'm saying.
I understood most of it. I assume though that like IBM owns that patent or
Rockwell
Rockwell.
Collins, actually. Yeah,
Rockwell.
I
Okay.
also I worked for I worked for IBM for about half of my career, and Rockwell Collins, which was more the avionics and military side of things for research.
Right. Okay.
IBM was more software and intelligent agents, a lot of these more advanced software type stuff.
Okay.
For the microprocessors, there's a number of ways you can mitigate the radiation effects. None of them are perfect, but actually, it's amazing. The older technologies work a lot better. You think about Voyager, which was built in the 70s,
Right.
probably with 1960s technology,
Yep.
and it's still working today, even after being in cosmic radiation for what's that now, 50 years? So 40 to 50
Yeah.
years. And yet it's still working. They're having problems with it. They have to shut down systems. They've had to rewrite code, avoid memory areas that have been destroyed, but there are ways to do it. That's one aspect of the microprocessors. The other is trying to go to an asteroid, and you can't ship up enough microprocessors to do this job,
Right.
to do the restructuring. To build a huge space station out of an asteroid, you can't send enough. You could, but the cost would be prohibitive to send up 10,000 small robots, 10,000 microprocessors.
That would
It,
be
it,
prohibitive. Yeah.
so I avoid that. I send up 4 robots, general purpose type, with a lot of capabilities. I send up, I think it was 3,000 small systems, which include an advanced microprocessor. And the 4 robots, the general purpose ones, they build the framework, all the regolith, the rods and tiles. They build the frames and wheels, and they build that, and then they attach the electromechanical device to the framework and use some of this. So then you have not just 4 robots, but you have over 3,000 good intelligent systems that can work on the asteroid.
Yeah.
But you're still dealing with the radiation, you're still dealing with failures. And also, 3,000 robots is not enough to do the restructuring work. You need 10 times that. It would take you, instead of the 12 years I talk about, it would, with 3,000 robots, it would probably take 120 years to do that job.
That's too long. That's too long.
That's too long. So, how do we get enough computation capabilities up there? You start looking at what do these things have to do? Well, you have to move rock from point A to point B. That's a pretty simple thing. You could build a little truck and you could have the robot, and I sometimes call him Spider, you could have the robot push it from one point to the other, or you could turn it into a mechanical automaton,
Yeah.
which with gears, levers, think about a cuckoo clock. With a very simple mechanical device, you could set a couple of levers. The smart, intelligent robot could set a couple levers, and the truck with regolith in it would know, okay, I need to go a certain distance, take a right, go another certain distance. There's a lot of work to be done that's at that simple level
Yeah.
that you don't need a microprocessor to do. You just need a small mechanical state machine. You can set the levers, and then it proceeds to go off and does the work. Guess what? Those mechanical state machines aren't affected by radiation, or
No.
minimally. So you
Yes.
don't have to worry about that. You build those at maybe a millimeter tolerance. F that. You don't need a high precision tolerance. Unlike a silicon line, you need at least micrometer type uh,
Right. Yeah.
resolution to build those. So all of a sudden, you have a system that is easy to build, not affected by radiation, and yet can do a bulk of the work for the asteroid restructuring.
So little truck is assuming there's gravity, right?
Yep, yep.
Asteroids don't have a whole lot of gravity.
No, they don't.
So it's not just a little truck, it's a little truck that also holds itself down on the asteroid, right?
Right. And that would be a challenge. And even going across the asteroid with
Hmm.
rocks and stuff would be difficult. And then telling it to go from point A to point B on any surface, on the Earth or on the moon or on asteroids, you got things in your way. It'd make the navigation very difficult. So, and you'll find this in the paper, one of the things I advocate is the first thing you do when you start setting up this system, you start laying down tracks. You build a truss that has a 1 meter width
Okay.
on the spacing of the top of the truss, and then you proceed, you pick it up, you slam it over, and at the end is a post that digs into the asteroid. And at that point, you now have the two rails for vehicles to roll on. You literally cover the entire asteroid or much of it with these rails, with the tracks. And the tracks, you brought up a very good question. How do they stay on there? When I wrote the paper, I'll say I kind of just glossed that over a little bit. I assumed there's a little bit of gravity, it'll stay on there, but that's a little risky. So the more modern thoughts to this date are you would proceed to have, just like railroad tracks, you'd have bars going across on the top of the truss.
Okay.
And so you have the two rails for the wheels to go on. You have crossbars, which help with it being more sturdy.
Yep.
And it also gives the truck or these other devices something they can grab onto, pull themselves forward, grab
Oh, yeah.
onto, pull themselves forward. And oh, by the way, while you're doing that, you also, behind you, keep a hold of the bars to keep you on top of the track so you don't go flying off if you catch up too much speed. And for example, digging, there's been a lot of research on, for example, how to dig with regolith. And when we start digging down, that pushes you up. So how do you do that? And a lot of good research on that. And some of those ideas are worthwhile, but I'm trying to keep things as simple as possible. You've got this track, so you're locked onto it. Well, you can now start digging and pulling stuff into the truck
Hmm.
because you are pulling yourself down onto the track.
Yeah. Once you've got the track built, and things are
Yep,
a little more
that's
dicey until you've done that.
in the simulations. That the first thing I would have the spiders first take a few samples from right near the seed. The seed lands. It tends to lower flaps down, the protective shielding on it. which then gives you a base to operate on. And so then you can go off to the edge of those flaps. The spiders
Okay.
can shovel up some of the regolith, take it back to the seed station. It has the ability to process the regolith and start producing rods and tiles. That
Okay. Yeah. Okay. That's not making sense. When I read the paper, I didn't quite catch that that's what you were doing.
that's the problem with trying to push too much into one paper. It really would have been better to ideally either put it all out in one huge book or a series of papers. And so that's what I'm doing now is I'm taking different topics from that 60-page paper and expanding it out to more detail. I'm maybe one thing I might get from people that view this video is I'd really like to see more on how you're going to build your web, build your the tracks over the asteroid.
Good. You mentioned the simulations. This is how you're testing out your ideas. You've got a computer simulations. Pull up 3D, or how you doing the simulations?
They're discrete event simulations. This isn't testing. There's lots of different simulations that a person does. The one that I was focusing on is how long will it take to build this space station? I take all the different tasks that have to be done, and I either find similar tasks that are done by NASA or by other scientists, and I come up with a metric on how long would it take to melt regolith, let's say. Okay. And I get a number of different answers. I take something conservative and I use that as for melting regolith, here's how long it's going to take. For extruding a rod, here's how long it takes. For moving across the track, how fast would a truck roll across the track?
Yep.
And I've taken all those different timing metrics and for all of the different devices in the system and discrete event simulation, it says, okay, what's going to happen in the next unit of time? And
Okay.
initially, you only have a few things that are going on. How long does it take for those flaps to fold down? Okay. At some point, some things you don't even bother measuring because it's too small with relation to everything else.
Right.
So that's the biggest simulation. But there are other simulations that you need to do. I haven't done any material studies, for example. How strong are these rods and tiles of regolith? But I have found previous research that's been done on the exact same type of regolith,
Yep.
and they've done all the tests. A lot of these were done in the 80s and 90s. I don't need to redo that research, so I use a lot of existing research results for my simulations. A lot of what I've done is similar to what other people have done, but best as I can tell, no one has come up with combining all these ideas into what I've put out there as a paper.
Yeah.
I run into this all the time. People say, let's use a rail system to launch stuff off of the asteroid. Well, that would be nice, but we don't have the magnetics. It just doesn't work for the kind of system I'm working on. The whole system is based on using technologies from the 1800s and the 1900s.
Right.
You think about what could be done in the 1800s, and even by the early 1900s, they were building Eiffel Tower or
Yep.
the Empire State Building, or both
1800.
around that same time frame. But they're using technologies that did not require electronics, did not require massive amounts of electricity, and did not require highly refined ores or semiconductor parts. And that's the type of technologies that I'm trying to use in this system is strictly 1800s and 1900s. I'm not the only one to have come up with that idea. Philip Metzger is a researcher, and he also put a paper out that he talked about bootstrapping. So he talked about going to the moon with a small seed
Hmm.
and starting to build technology, starting out with technologies from the 1800s, and then with those technologies, build things from the 1900s, and using those, you go into the 2000s. He had a path on how to get to very modern day type of approaches. It's great, but he required a regular shipment of materials in order to accomplish this. So as he's going along, you keep on shipping more materials, some special type of acid that you need to do your semiconductor processing.
Oh, okay.
Okay. Or an e-beam technology would be the later type of years, but some technologies that would be very difficult to build on the moon, you just send them up there and then you
Right.
have it available. But he started off with the same premise as I did, which is you start off with the simple technology, use that to build up. And quite often they're talking about, okay, to build the first place structures, enclosures for some of these technologies. You can do that with 1700, 1800 technologies. You can
Yeah.
build a habitat of some sort on the moon or somewhere. Well, that was my goal, is not going any further, but just getting to the point where you have the space station developed with just these earlier technologies. Now, when the space station is complete from the restructuring point of view, it is not airtight. Not yet. It would require maybe some plastics, some other type of materials. But
Right.
what the restructuring finishes, you have a rotating space station. It's
Hmm.
rotating, so you have gravity. You're not going
Yep.
to have the microgravity. Microgravity is bad for the human body.
Yes.
Um,
My next explainer videos talks about that actually.
Even 5 years ago, they weren't certain whether even moon gravity would be sufficient to prevent all these damages. And it turns out they just finished some studies on mice from a study done on the ISS. And no, moon gravity isn't enough. You still have your bone density goes down. So if you stay
Right.
on the moon too long, it's not going to be good for you. And it's even worse for children, I'll say.
Yeah.
Now, the next question is, well, what about on Mars? Will you have the same problem on Mars with the zero point 0.4 Earth gravity? What do? Moon and Mars are the two big areas that they're saying, well, let's set up colonies there. Well,
Yeah.
gravity is bad. And also, radiation is bad.
Yep.
So the space station is rotating. When the restructuring process that I talk about is done, it's rotating, so you have the gravity. You also have very thick shields. You got
Yes.
lots of material on the asteroid. So I had 10-meter or 20-meter thick
A
outer
lot more
outline.
than O'Neill was ever talking about, I think.
Yeah, he was talking about 3 meters, which
Something like
that's
that.
good. But if you got the material, and if you really want to stop the radiation, and if you want it to be structurally resilient to micrometeors or to a space shuttle that happens to go veering off and runs into it, well,
Oh, ouch.
yeah, ouch. It comes from the avionics business. You worry about things like that. How are you going to overcome a catastrophe like that? And O'Neill talks about it too. One of his solutions was you set up the torus into about 6 different segments, so that if one of them gets wiped out, you still have the other 5 segments.
Yeah. That's good for the people in the other five, not so much for the
Right.
people in that one. Yeah.
In the avionics business, nobody would say, okay, so if we only lose 1 out of 6 planes, that wouldn't fly at all. The very thick outer portion of the station, that has a lot of good advantages to it. Number one is the radiation, for me, that I was worried
Yeah.
about. And then see, suddenly now you have no radiation, you have gravity, and now you can send up some of the first, not colonists, but some of the first crews to help start sealing it, sealing stations, sealing holes, starting to install HVAC systems. That's the people that would start turning it into a livable habitat. But they're safe now. They can live in there. In fact, you could potentially bring along some of these inflatable type habitats.
Right. It's a big, just a balloon kind of thing, and then you're just inside of it.
Right, right. Yeah. And so you could have one of those inflatable type habitats, and that's where they could live while they're starting to seal off portions of the station.
Yeah.
And you would build the station so that portions of it could be sealed off faster than the whole thing. So this is getting to the point where somebody could go up there and work safely was my main goal.
Okay.
And that's something I'll say. So
Yeah, and it'd be quite the adventure to be,
definitely,
to be
definitely.
sealing a space station to turn it into a home.
Yeah, yeah.
So
Um,
at that point, though, what do we do with all these spider bots and all of the trucks and stuff that they had built? Do we recycle them?
I haven't given that a lot of thought. I do
Okay.
mention a little bit that the Atira was the asteroid that I had picked out. It had a moon associated with it. So
Oh, okay.
as you start finishing things, well, very low gravity, you could just push it the right direction and you could start moving some of these robots and the mechanical automaton to a moon to help work it on that. And at that point, you've got a lot of material. You could start firing regolith off one direction. You could start moving the moon to one of the other, to another asteroid and start again. So,
Oh,
yeah,
okay.
reusing them is quite possible. That'd be an interesting paper in and of itself, I'll say.
Okay.
I'm refining this whole process and applying it to a smaller asteroid
Okay.
so that instead of taking 12 years to get it done, my current estimates are something more like 5 years to get a smaller station complete.
Nice.
Yep. And the smaller station, I do enough different versions, but it's easily almost 100,000 people instead of the 700,000 that I had for the paper that I wrote. But a
Okay.
smaller station, you can end up with being able to support
Nice.
70,000 people. It's interesting that one of the things that I added into the station design is using multiple floors.
Hmm.
Most stations that you see that people have done the research on, they don't do multiple floors. They might do 2 or 3 floors in the station. You don't want to vary the gravity very much. As you start getting to larger stations, suddenly you can have roughly 10% of the radius can be used for stories of the station. The one that I did, I think it had around 60 floors.
Oh, wow.
Um,
Okay.
yeah, and the gravity range is from 0.95 Earth gravity up to 1.05 gravity, a
Yeah,
restriction that I give on it.
that's a
And
pretty big
yet you
range.
can, it's safer than Mars or the
Yeah.
moon. We know the moon is bad now. That was the recent study result. I hope that the 0.95 to 1.05 Earth gravity will be safe for people. I believe it will, and you can always spend most of your time closer to 1.0.
You were talking about the Rama where it was all mechanical. So why would
Yeah,
you go electronic rather than mechanical parts for the seed?
for the seed, I'll say probably one of the biggest reasons is for image processing. So you got these intelligent robots that have microprocessors,
Mhm.
sensors, memory, full up computers. They're the ones that can set the levers, set the
Okay.
dials on the mechanical automata.
Right.
Someone needs to do that. A couple of us were trying to figure out how to build a sensor using mechanical parts. It is possible to do, but it takes pretty refined processing down to the micron type level processing
Oh,
of mechanical devices. At some point, you kind of go, well, it's a lot easier to use electronics for that.
yeah.
Most of the restructuring process, I have the 4 original robots. They're the ones that have full up capabilities. I then have 3,000 of the robots that were built with in situ material and with a few 20th century, 21st century technologies, some sensors, some radios. So you got 3,000 of those. And in the paper, it shows you need almost, I think it was 12,000 of the mechanical automaton,
Oh,
the
wow.
dump trucks, the flatbeds, the things to crush the rocks, all the mechanical type things. I don't use that much electronics. I mean, in relative terms, I'm
Yeah.
doing four full up, then 3,000 that are 75% mechanical and 25% electronic. And then you have all the mechanical automatons that are doing most of the work. They're the ones that are completely mechanical.
Hmm.
It's interesting to look at what the initial robots that land, those 4 or even
Yeah.
the 3,000, initially they're doing the work. They're the ones that are digging up the regolith. They're also even initially carrying it over to the seed station to help build the first rods and tiles and to
Yeah.
build some of the first structures. But eventually you start building the mechanical devices like the dump trucks, like flatbeds and crushers, the crushing of the rocks. Well, that It has to be done early because there's only one thing that can do the crushing of the rocks, and that's the initial seed station, or you have to build something to crush rocks
Yeah.
to prepare the regolith and get it ready for processing. So that's the order of things.
So how are you powering everything? Like solar
The,
panels,
the, well, solar panels
mechanical
for
winders?
mechanical what?
What like you have the certain robots winding up the other robots? Like
Both of those, yes, I'll say.
okay,
You don't send up solar panels, but you send up a lot of solar cells to reduce weight. And so one of the first things some of these advanced robots do is they start taking the frames, the tiles, and the rods, and they build a frame for the solar panels. Then they can put all the individual solar cells on it, and now you have solar panels. So
right.
solar panels don't cost that much weight if you can build it up there from the solar cells
Oh really?
themselves.
Okay, I
Yeah.
did not know that.
Uh, uh, I know the solar cells are very small and lightweight. I know the frames are very heavy. And so then all the electronics have the solar panels to run. Some things you need, for example, I talk about having a Fresnel lens,
Hmm.
which focuses light down to a point and can melt regolith.
Yep.
And you can also do welding with it between
Yep.
different pieces. So that Fresnel lens, well, that's nice, but guess what? You have to track the sun. The asteroid's turning, so you have to track the Fresnel lens to keep it on that one spot. That's something that the robot, with the sensor, with the electronics, it can do that quite easily,
Yes.
relatively easily. Unfortunately, you need to have thousands or tens of thousands of those things, or you have to have a lot of those growing, and you're using up kind of an important resource, the intelligence and the sensors,
Yeah.
to move the Fresnel lens to do the welding. That's where a clockwork mechanism could come in with a spring, hopefully derived from metal that it's recovered from the regolith. Build a
Yeah.
spring, then, as you had just said, the robot can wind it up, and then it can slowly click, and the Fresnel lens would track the sun and weld spots. So there are some clockwork mechanisms for power. But then the third one, which is probably the biggest amount of power, is something called a Stirling engine.
Okay.
Okay. This is a technology from the 1800s. It's a very simple, this is before steam engines, which required very tight compression fittings, very tight, very rigorous metal. In order to build steam engines, they had something called a Stirling engine, which was a low pressure atmosphere that you heat up or you cool down and it moves a baffle.
Okay.
Okay. And as that baffle moves up and down repeatedly with the changing, guess what? On an asteroid, you've got hot and cold.
Yeah.
I mean, in the shade, it's cold. In
Yep.
the sun, it's hot. So, relatively easy to get hot and cold. So, the Stirling engine provides mechanical rotational power. And once you have that, well, you can gear that down to a truck wheel or
Right.
to the mechanical contraption that grabs on the rails and pulls yourself forward.
Yeah.
And I've seen up to 5 horsepower for some of these Stirling engines, which it's not a lot, but if you're gearing things down, if you're not in a hurry, you can move a good quantity of weight with a
Yeah.
Stirling engine. And you're on the nice rails, which are nice and smooth, and it's fairly straight. It's not that hard to move things down the rail compared to trying to move things across a rocky surface. There's a lot of different ways to get power, but how do you do it using 1800s, 1900s technologies?
Yeah. So going a slightly different tack. So you've built this space station. Are you leaving it in orbit where the asteroid was?
Yeah, when I started, yes, I'll say the short answer to that is that was the original plan. How's that?
Okay.
Originally, I was planning this to use almost all of the asteroid to build the station.
Yeah.
That was the initial plan. Okay, so then you just leave it there in the same location. It turns out that you only need about, I think it's 30% of the asteroid to build the space station in the paper that I wrote.
Oh, really? Okay.
Yep. So all of a sudden, well, you got a lot left over. A challenge that I address in the next paper, I'll say, is how do you move the station away from the asteroid? Because the asteroid is moving at one rotation rate and your space station is rotating much faster. So eventually the two don't quite mesh together very well.
Yeah. Okay.
Because the asteroid can only go at a certain speed, otherwise it starts to fling off its own material.
Yep.
These are the rubble piles that they talk about, and yeah, and the rubble piles only go up to a certain size and a certain rotation rate, and they haven't found any other asteroids that are rotating faster than a certain size for rubble piles. Because
All right.
otherwise, if you're rotating too fast, it just disintegrates. It blows off parts of the asteroid. So you have the same problem is, okay, we want to spin up the station to the point where you have one Earth gravity, and the asteroid only has 100th of a Earth gravity. They're rotating at completely different speeds.
Yeah.
So you want to be able to spin up the space station close to the asteroid. You need its material, but eventually, my opinion is you want to move it away. So a couple of a friend and I are working on that right now on how to spin it up and move it away. I do talk about how to spin it up in the paper. Those are fun questions.
I'm imagining like you've got your torus that you're spinning, or you're trying to get spun up. And you just if you're always sending from one side, it'll
Uh-huh.
slowly move and speed it up at the same
And
time.
speed it
But
up. Yeah. Yeah. I wonder. Yeah, you might be right. Yeah. What I was envisioning is so you got the torus, and I had the asteroid inside of it. You can fire material from the asteroid up to the rotating torus
yeah,
shell. This is before it's complete. The outer rim is complete. You can start sending up material. Hopefully, you have the space station rotating fast enough that there's some simulated gravity there, and it would hold the
yeah.
rocks. But it turns out the asteroid is so much heavier than the space station that it barely slows down. It's
Mm,
conservative of rotational momentum. You're taking a little bit of the rotational momentum from the asteroid and giving it to the space station to speed it up. And as you were worried about, yeah, you put these launchers at regular intervals around the equator, and they're all firing. You end up with good forces equally. You're not going to
yep.
push the space station, have part of it move away from the asteroid and part of it moving into the asteroid, which would be bad.
Yeah, you don't want that.
No,
Since we got onto this topic, what's some of the new things that you're talking about, you're studying for the
um,
next paper that you're writing?
I'll mention two other papers that I did already put out there, which one is rotational balance space stations. If you design the space station wrong, there's a risk that it'll become unbalanced and actually catastrophically start tumbling.
Oh,
Um,
yeah, don't want
yeah,
that.
Al Globus did a paper on that quite a few years ago, and he talked about the O'Neill cylinders, very long
Yep.
cylinders. Those aren't rotationally stable. There's a risk that they could start tumbling. So he and his students they did an analysis, and it turns out instead of a long cylinder, you make a short, squatty cylinder,
Okay.
and that's rotationally stable. The Kaplana station,
Which
a
is
space
yeah.
station that they were working on, and the whole reason that it's a short, squatty cylinder is so that it's rotationally stable.
Oh, okay.
So I put out a paper that has all of the geometries. When are they stable? When aren't they stable? And I added in what happens when you add in multiple floors to the station. Because guess what? All of their analysis is on a thin shell.
Right.
Okay. And I've got these thick shells and I've got all these multiple floors, which add a lot of weight right at
Yep.
the equator, right on the outer side. So it changes the rotational stability. So that paper is out there. That I found an interesting one. And again, this is just math for the fun of it, physics. The other was how big can you make these stations? What are the limits? And there's a
Yeah.
number of papers on that, on what size you can make them. I put one out there and adding in one other topic to it, which is as you start getting to very large stations, over 10 kilometers in radius,
Yeah.
all of a sudden you have multiple stories. You've got a lot of stories. It gets so tall that you're up a mile high, like 1,300 meters high.
Mhm.
Well, guess what? if you've been to Denver, some people have trouble breathing in Denver, and if you go much higher up into the mountains, the air gets too thin. So there is a restriction on these stations that you can't make them. You can't go past a certain size before air pressure becomes a limitation.
Right. Yeah.
Just consolidated all the information, talked about the background on it, and that's out there. Current one that I'm working on is agriculture for these stations. O'Neill, in the NASA paper, had an extensive part on the agriculture that would be in their station in the space settlement paper. I've been looking at their numbers, and it doesn't appear they include enough agriculture to support the animals that they have on the station.
Oh, okay.
I've tried to read it multiple ways. I've tried it, and I'm doing my own math on it, and it
Yeah.
seems like it comes up short, and by quite a bit. So I don't know if you can have cows on a space station because of their feed requirements.
Yeah.
So,
They
so anyway, it's an interesting
have to build a
endeavor.
separate station just to put cows on type thing.
There you go. Yeah. So, yeah, and fortunately, nowadays there are new ways. You can actually grow beef cells, biologically generate meat from cells. You can grow the cells and create beef that way, which is being done today. It's a option that you'd want. It's much more efficient than a cow, I'll say,
Okay.
with regard to feed and with regard to water use, a whole set of good things from that. So anyway, agriculture is an interesting topic. And then one that I've been working on a bit is a smaller station, one
Right.
that can be done in 5 years and address some of the open issues that, in my mind at least, on the paper, like how do you move it away from the asteroid without crashing?
Yeah.
Um,
Building it and then crashing it would be a bad idea.
that would be a bad idea. Those are some of the top items, I'll say.
Okay. I think that was all of my prepared questions. Was there
Okay.
any questions that you think I should have asked you that I didn't?
Hmm. Yeah. One thing that no one ever seems to ask is, okay, what's wrong with this approach?
All right.
I mean, because guess who knows? The
The
person
person who
that's been
designed it.
researching it for the last 5 years, they know its weaknesses, they know its problems. I've
Right.
talked about a number of them. Some speakers might get a little upset at that question, but I think it's a valid question for anyone giving a talk is what's missing? What's wrong? You did ask some of the questions that you previewed with me. What's the technology breakthrough that you need in order for this to work?
Yeah.
There's a little bit of, I'll say, standard research that needs to be done. But in my mind, there aren't any showstoppers on this approach.
Okay.
So, two-part question. There was the question that you should have asked, and I think I've answered it. There are some other issues, but still no showstoppers, I'll say.
So, what are the other issues that you're studying? Like agriculture, you
Um,
said.
Agriculture is one. How to move it away from the asteroid. It actually turns into a bigger issue than I originally thought, than I documented.
Oh,
Believe it or not, nitrogen is a problem.
nitrogen?
Nitrogen, yep.
Why?
Yep.
Why is nitrogen?
What are we breathing as you and I are speaking right here?
It's 90% nitrogen.
The atmosphere that we breathe is close to 80% nitrogen.
Yeah.
And that's a lot of nitrogen. The different type of asteroids that we're targeting, the C type and the silicon type and the carbon C type asteroids,
Right.
they don't have a lot of nitrogen in them.
Oh, okay.
Uh,
So, like, nitrogen would have
so,
to come from somewhere else if we wanted
or
nitrogen.
right. The reason is that nitrogen is a fairly lightweight gas and it actually gets stripped off by solar radiation with comets and with asteroids. There's plenty of nitrogen on asteroids like Ceres and the moon, some of the moons around, is it Titan? I think that it has
Hmm.
a huge amount of, some asteroids will not have enough nitrogen to support the air in the station. In which case, okay, so do we have to send some from Earth up there? That kind of violates one of my premises that you want to do everything using asteroid material. Or it might mean we need to send a couple of surveys to say, okay, what is the material that's on this asteroid, and is there going to be enough nitrogen?
Right.
It sounds like a trivial problem, but other than a wish and a prayer that there's enough nitrogen on the asteroid or in the rocks and the material, which is possible, it's possible that there will be enough. But
Yeah.
you look at the standard metrics that they've done through the light surveys, the light measurements from asteroids, knowing what the surface contains, many of them won't have enough nitrogen. So it's an issue. And I have not seen anyone address that problem. So I don't know if I'm making a mountain out of a molehill or if everyone has just said, oh, don't worry about that. We'll deal with that problem later.
Well, I think O'Neill was saying like we don't really want to use nitrogen, so you wouldn't get the bends if you had a sudden depressurization. But
What I remember, I think he does say that they would ship nitrogen up to the station from Earth. They would send
oh,
bottles of nitrogen or frozen nitrogens. They would get it up there. Nitrogen is bad, it gives you the bends, but it's actually because the nitrogen in your bloodstream starts boiling. But if you don't have nitrogen, you need to replace it with something. Human body can't breathe pure oxygen, which is also a little dangerous when it comes to little sparks.
I
But
think the idea was to use helium, but I could be wrong about that.
uh, everyone would be talking like this then.
Yes, yes, indeed.
I guess you get used to it after a while. So, but
I guess
yeah,
maybe
so
you even learn to speak lower toned.
yeah, most of the challenges with this are doable with a modest amount of research. I've mentioned this NASA paper on the space settlement multiple
Mhm.
times.
Yep.
That was 30 researchers, one summer for 10 weeks, is what NASA funded a lot of researchers, including O'Neill. O'Neill was the technical director on that NASA study. That was 6 man-years worth of work, is what they did to create that document. And they also probably had a lot of backup material and
Yeah.
students back at the university. This was research professors from across the nation. They probably had students back at their university that were helping too. They did a lot of good work in 6 man-years. I've been working by myself, and in about 5 man-years, I've been able to create something close to what they had, but a completely different approach, I'll say.
Yeah.
So, or a very similar approach. So, it needs a focused effort by experts in the field in order to get this up and done. I've stated it in the paper multiple places that this isn't perfect, but you got to start doing something. And I do try things out multiple times. Rapid failures. That's the way to create good progress. And I think this is almost at the point where doing some of this work, maybe on the Earth, for example, would be a interesting thing to do. It would be fun to start building some of these mechanical automatons using 3D printing.
Okay.
Um,
Yeah.
it would actually be a interesting challenge for high school students or undergrad students. I think it's completely within it, both in the mechanical area, mechanical engineering area, or
Yeah.
in some of the space studies. It seems like there's a place where this would be valuable. And I can get hold of a 3D printer. I can do that, but I've got this long list of things that I need to do. So I'm at the point where please help me.
Okay. Yeah. Let's see if we can get you your help.
That'd be great.
So just to wrap up, how was this talk? You enjoy yourself for the last hour and 20 minutes?
I did, yes. You start talking about this stuff to your friends, I'll say, that you go to church with, or you talk to your dentist about it, their eyes glaze over, and it's like, what's he talking about? So it's great to have someone who understands a lot of these technologies, the issues, and can actually play off of what we've been talking about and ask good questions. So for me,
Yeah.
it's enjoyable that, and again, I have a couple of people that I'm exchanging a lot of good information with, and they're making good progress on some of these issues. So it's been fun to do. But I enjoyed the talk. How's that?
Okay.